So, hello everyone. Myself Sudipta, Hensh, PhD student of Institute of Physics, Silesian University in Opava. And it's my pleasure to present my research here in very special RAGtime. The work was done. Uh, the work, strong gravitational lensing around Kehagias-Sfetsos black hole surrounded by plasma, was done in collaboration with Yanse, Ahmadjan, and in collaboration with Professor Stuklik. So here's the overview of the talk. I'll talk few sentences about the motivation behind our work and then the geometry in which we are working and how geometry gets modified due to the insertion of plasma, and then few models of plasma which we are considering. And next, schematic diagram of lensing and the brief overview of deflection angle formulation by Bossa. And next, image position and magnification, and next section, observable quantities, and then I conclude our finding. So as we know that Horaba gravity is very interesting because it is a candidate of quantum gravity. So from observation, we can hope that Horaba parameter could be constrained. And on top of that, we also want to see how plasma affects the strong lensing when we change plasma parameter. So here in equation 1, we see the line element of Kehagias-Sfetsos metric, which was done back in 2009 by Kehagias and his colleagues. This solution is basically we get a Schwarzschild solution when omega tends to infinity, and this solution is a metric is singular basically when fr is equal to 0. The roots of this equation as you see here. So black hole exists only when this Horaba parameter greater than 1/2 m square. Otherwise it is naked singularity. So the actually photon doesn't follow the geodesic in the background spacetime when there is plasma. It follows rather the effective geometry corrected by this expression 2. This was found by Singh in 1960. And we are considering here that plasma doesn't have any velocity, that is it is in rest, but so only temporal component of the velocity will be non-zero. And considering this kind of plasma, only temporal component of the metric will be modified as in 4. So models of plasma which we are considering is, we are considering mainly two kinds of plasma. And the refractive index of plasma is given in 5, where this omega E is the electron plasma frequency and omega pH is the frequency of photon. And N is the number density of electron, which is proportional to the square of electron plasma frequency. And at first, we consider the model without any existence of plasma. So this is basically a reference to compare our results when we insert plasma. So model B is when the electron number density is falling 1/r. So we get n square as in 6. And this is the schematic diagram of lensing, as you see here, where this position of observer is at O and lens is at L. Lens is basically the black hole in our consideration, and source is behind the lens. That may be some stars or something else, and image is formed at I. So here beta is the angular position of source with respect to optical axis OL, and theta is the angular position of image with respect to optical axis OL. And B is small b is the impact parameter, and x naught is the distance of closest approach. So deflection angle given in 7 was calculated by Bosa. This is an approximated expression for deflection angle, but it is very useful because it has some very good numerical advantage. You can calculate it very easily compared to the analytical formula. And the other L gamma is impact parameter of the photon orbit, and A bar and B bar are given in 8 and 9, which can be calculated using space-time parameters. Here index 0 means it was calculated at turning point, and index gamma means it is calculated at photon orbit. So other R and beta tilde gamma are given in 10 and 11. So we see that in B bar, BR is the only numerical integration which we have to perform in order to get the value of deflection angle. So which is given in 12, and the other parameters are given in 13, 14, and 15, which I'm going through very quickly. So here in equation 15, A tilde and B tilde are given in 16 and 17, and Z and AR are mutually connected with this transformation given in 18. So the equation 19 is a length equation found by Bosa using strong deflection limit. And this delta alpha n is basically the offset of deflection angle. So if photon winds up n times, so how much it deviates from the deflection angle, that is the measure measured by delta alpha n. And angular position of nth order image is theta n, which is given in 21, and where alpha theta n0 is it is wrong because it should be n and subscript should be n. Okay, so theta, for those theta for which deflection is exactly the multiple of 2 pi, and hn also given in 22. So following the definition of magnification 23 and applying the space-time parameters considering strong lensing, we found the magnification of nth order image that is given in 24. So observable quantities which are of astrophysical interest are angular separation of first order image and infinite order image, because the higher order image higher than 1, they are already collapsed, resolved as one image, and the higher order images are collapsed as a single image. So we can distinguish between first order and higher order images, that is theta 1 minus theta infinity, and the parameter is s. And is also important to define some quantity by same logic, that the magnification of first order image and the sum of the magnification of higher order image, that is defined by R given in 26. So using space-time parameters, we get expression of S and R given in 28 and 29. So how this deflection angle depends on A and B, that we know from relation 30. So here we want to see how plasma is affecting the strong lensing, or how it affects. So from figures, we see that when we increase plasma parameter, A bar is decreasing and B bar is increasing. So that means here we see that, and we didn't show here, but L gamma is also increasing when we increase plasma parameter. That means the terms inside logarithm is decreasing. That means overall this deflection angle is increasing when we increase plasma parameter. And this is the variation of angular size of infinite order image as a function of ks parameter, omega parameter. So when we increase the plasma parameter, we see that the angular size of image is decreasing. Basically, this theta infinity is the angular size of black hole shadow. And the parameters which we use are that black hole mass of m equal to 6.5 10 to the power 9 solar mass, and the distance from observer to lens, that is 16 megaparsec. So here angular separation of image as a function of ks parameter is presented. And we see that when we increase plasma parameter, this angular separation, that is the separation between first order image and higher order image, that is more evident when we increase the plasma parameter. And the plot of relative magnification of image, that is the ratio of first order image and higher order images, sum of higher order images, that we see that when we increase omega parameter, that is Opava parameter, then the plasma effect is more evident. So for higher value of omega, this plasma is kind of increasing the relative magnification. And here the conclusion, which I have already told, that the deflection angle increases due to the effect of plasma, and plasma also reduces the angular size of black hole shadow, and angular separation of first order and higher order images increases because of plasma, and relative magnification is increasing for higher value of Opava parameter when we increase plasma. So it is possible that we see from observation R and S, that is the relative magnification and angular separation given in 28 and 29, and also theta infinity. So from 28 and 29, we can find A bar and B bar, and A bar and B bar are the parameters of space-time. Like we can, so from 8 and 9, basically we can find what could be the value of omega. So in principle, we can find some constant on omega, but for detailed analysis and exact putting exact constraint, we have to consider some more sophisticated model, which we are planning to consider some sophisticated model of plasma distribution and all that. And these are references which I have already shown while showing slides. And thank you everyone for attending the talk.
Thank you, Sudi, for your interesting contribution. And I would like to ask audience for questions. So you are free to raise your hands or chat. Okay, if there is none yet, maybe I can ask my question. Sudi, can you describe in slightly more detail how, what is the advantage of this strong limit of deflection angle?
Yeah, you mean?
Yeah, well, actually, why the expression for integral BR is that good?
Yeah, because it is a regular integral. There is
Yes.
Yeah, and if we consider analytic form, then actually the actual deflection angle, analytic deflection angle, we can divide in regular and divergent part.
Yes.
So this BR is regular part, and we can integrate it numerically very easily. So this is kind of numerical advantage we have in this form.
Yes, yes. Thank you. Still no questions?
Well, if I may, yes.
Yes, yes. Okay.
Yes. So I have to confess I got lost in the algebra. So can you tell us what a singularity would look like?
Sorry?
You're discussing the image, right, or the shadow, or whatever. So I'm wondering about this singularity solution. What would the image look like?
Sorry, I didn't get.
We were considering the black hole.
Singularity?
Yeah, now.
For naked singularity, but for now we are considering only omega greater than 0.5. So.
Oh, I see. You're only doing the black hole. Thank you.
Yes. Yes.
Mm-hmm. Thank you.
Okay, thank you for question.